Good morning, everybody. Welcome back. So these are the survivors of the 4-day weekend right here, right? Yeah. Half of you are going, what weekend? I don't remember a weekend. We're going to jump right in this morning and get covered. Come over here. Give me just a second, everybody. If you have any questions, just interrupt me, okay? All right, so we're gonna jump right in and keep going on the Newton's second law stuff, and hopefully get started on chapter 6 today. I know that feels kind of fast, but chapters 5 and 6 really should be the same chapter anyway, because in chapter 6, what we're gonna do is we're gonna add friction into the mix. So I want to do an example where there's not one, but two objects. Those objects will be connected together by rope, string, a chain, introducing the force of tension. And it's going to have a pulley in it. So, I mean, we could baby step our way and just talk about pulleys or just talk about tension. But what we're going to do is we're going to just kind of put it all together into one worst case scenario, right? Again, for you to use as a template of method, right? Not necessarily that the equations we developed will be useful everywhere, because remember, with a Newton's second law problem, we develop the toolbox on the fly. The toolbox changes for every single problem and situation. It's the method we apply to generate the toolbox that matters. So keep that in mind, right? Try not to laser focus on the result. Try to focus on the steps and method that we're going to use. So here's kind of the most, generic version of this that I think I could probably come up with. It's going to involve a hill. And what do hills look like in physics? They always look like triangles. Whoops. That's not going to work. Okay. Hill. Something like that. Okay. So there's our hill. And we are going to have two objects. So I'm going to call them mass number 1, and I'm going to call them mass number 2. They are going to be connected together by a string that runs over a pulley. All right, so we need to talk a little bit about strings. Where is it? Right there. All right, what do we call the force that a string imparts to things? Tension, okay? Talk about the tension in a string, right? The reason that we give this force, this push or pull, a special name is because it can't push, right? Tension can only pull on things, right? As soon as we try to push with a rope, it doesn't work, right? Okay, so that's kind of the distinction there. But tension is just another name, a label for a force that's already there. And what is the object that causes tension always? It's the string, it's the rope, it's the chain, right? It's the thing that's connecting two objects. In this case, maybe the ball and my hand over here, right? It's just another name for that pull in this case, right? Because tension can never push. And that gives us a clue about the direction that tension will act on objects. The pulley here is, okay, first of all, the string is very special. It's physics string. So what does that mean? It has no mass, okay? So we'll just go past weight all the way to mass, right? Doesn't matter where we are in the universe, doesn't have any mass, which is good because we don't have to consider the mass of the string in any of our calculations, okay? The other thing is it never breaks, and it also doesn't stretch. What that means is that the force is consistent all the way through the string or the rope or the chain. The pulley is a physics pulley. So by those same rules, what's the mass of the pulley? It's 0. And how much friction is in that pulley? None. Okay. So rightfully so, you could be sitting there going, oh, this is the dumbest class ever, Mr. Bailey. You're just making everything up because there's never any frictionless pulleys and there's never any massless ropes. Oh, yes? I'll show you some in lab, not this week, but next week. Okay? Next week, you'll have to remind me because I'll probably forget, but when we're in lab next week, be sure to have me show you physics string and physics pulleys. I actually have some, and it's not a gimmick. Okay? It's not make-believe. I actually have the real deal, right? So we'll get to that later. All right, so in this case, the pulley in this problem is merely changing the direction that the force is acting, right? The force initially is being pulled up the slope, and then it just turns and is acting in the vertical plane. So that's all. And I was going to say don't worry. Do worry. Because when we get to chapter 10, we're going to fix this. And we'll start introducing real pulleys. Okay, so this is our setup. This could be a ski lift. This could be a weird kind of elevator. As a matter of fact, if this were an elevator, what would we make the angle of the hill? 90 degrees, right? And then we would just have a counterweight system over a pulley block, right? This could be a piece of gym equipment, right? Like there's lots of situations where you'd have tensions connecting two weights and there's like a push-pull kind of situation going on there, right? So that's kind of this overall template we want to talk about. Two objects that are interacting with each other through the force of tension, and we're throwing in pulleys for good measure. What is our approach? What do we start? What do we do when confronted by a situation like this and we want to learn everything there is to know about this system? Where do we start? Free body diagrams, right? Okay. Now, you're going to see me cheat a little bit here because technically a free body diagram means I should take like mass 1, come over here and like draw mass 1 all by itself, right? To make it free, to make it not touching anything else. I don't like doing that because I tend to forget forces if I do that. So I'm going to leave the picture as is, but I'm still going to capture the essence of a free body diagram by focusing just on mass number 1 and the forces acting on it. And then I'm going to do the same thing by looking at mass 2. I treat them separately, right? They are interacting with each other, but I need to draw a free body diagram for each of the main actors in this particular problem, which are mass 1 and mass 2. So, which one do you want to start with, mass 1 or mass 2? Mass 1, all right. So what do we got? Name an object that is pushing or pulling on mass number 1? The string. Okay, so the string's the object. Good, you led with the object. That's great. What's the force? Tension. Okay, which direction is tension acting? Remember, strings can only pull. It has to be up the slope, doesn't it? Because a string can't push, right, on an object. So we have a tension that's going up the hill. Okay, name another object that's pushing or pulling on the mass. Even though I didn't draw it that way and they should be touching. Okay, you named the force. Earth was the object, right? And the force is gravity or the weight of the object, which I draw as mg. All right. Anything else? Good. The surface of the hill. You guys keep going for forces first, which is fine, but be sure you can name the object. What causes the normal force? The surface, right? Surface of the hill. Good. Anything else that's pushing or pulling on mass number 1? You've either already gone to sleep or you're running out of objects that are pushing or pulling. What do you want to do? Like what are you itching to like draw on there? Friction? Okay, there's no friction. You'll stop itching about that in about 40 minutes. Oh, so you're going straight for the components. We haven't kind of gotten there yet, right? because we haven't talked about coordinate systems or anything. We're still focusing on what could be pushing or pulling on mass number 1. We've got the earth, we've got the hill, we've got the string. Any other objects? Nope. That's it. Okay, try not to invent things. Let's go ahead and finish up the free body diagram on mass number 1. Okay. So we don't know, right? We don't know how this thing is moving. We have no idea what the velocities are. They could have started at rest. It could have been moving to begin with. Different problems will have different situations. But remember, free body diagram doesn't tell us anything about velocity or motion. It tells us about how the motion is going to change. So if I were to ask you, which way is the motion changing for mass number 1? Which way is it accelerating? Do you have a guess, an idea?
Guess is accelerating uphill.
Okay, so you're guessing pulling uphill, right? It's being sped up in the uphill direction, right? Which means it could be moving downhill but slowing down, right? But like, you're guessing that it's going to change its motion uphill. All right, does anybody have a different idea? We can't know, you're right, but is there another direction that somebody saw maybe instead of uphill? Downhill, okay? That's really it, isn't it? The whole point is that the acceleration is going to be up or down that slope, isn't it? We don't expect there to be any, like the mass is not going to be lifting off or digging into the hill, right? We know it's going to be stuck along the incline of the hill. So that gives you a clue of like which direction you want to guess for your acceleration. I know you get nervous when you start guessing, and some of you are like, but Mr. Balogh, I'm a practiced guesser. I've just guessed my entire school career. We have to choose, like one or the other, up or down. But the point is it's along the hill. It's along the slope, right? It's not in any other direction. Let's pretend we guess wrong, right? We go and solve our equations. Can you guess what might happen if you guessed the wrong direction? You'd end up with an opposite sign, right? If you ended up with a negative acceleration, it just means that your acceleration is opposite the direction you called positive. That's it, okay? So when we're looking for acceleration and we're not given any information about it, we choose. We just choose something that is friendly and nice, and that would be along the slope. I'm just going to go with the upwards one because it's what I heard first, okay? Again, doesn't really matter. What matters now is how we choose our coordinate system. If we're guessing that the acceleration is up the slope, then what should we put down for positive x? Always follow the acceleration, right? It's going to make writing down our equations easier. So we'll say positive x is up the slope, and we'll say positive y is away from the slope, perpendicular direction. And now this free body diagram is ready to go, right? We can start finding components. We can start writing down equations. Okay, let's go to the other free body diagram, mass number 2, okay? And give me an object that's pushing or pulling on mass 2. Earth, all right, so gravity. It's kind of the gimme, right? The giveaway. So, oops, you know what? I should come in here, and I was very sloppy. This should be M1G, right? Because this one's going to be M2G. They are different masses. Okay? Another object is pushing or pulling. Emphasis on pull. There is the string. Acting which way? It can only pull, and so that means it can only pull upward. And you'll notice there that I also said that that was T. When you have a massless, frictionless pulley, a pulley that's not affecting the system in any way other than to change the direction of the tension, that means the tension is the same. So the fact that the pulley isn't doing anything and the string is not stretching or breaking means that we can go ahead and set the tension to be the same everywhere in that string or rope or chain. That's the kind of the simplicity we're buying here. And again, we'll get to a point where those tensions will be different. That'll be chapter 10. But we want to do baby steps here at first. And some of you are out there going, baby steps? This is nothing like baby steps. This is like drinking from the fire hose. I'm like, I've got bigger fire hoses. Okay, any other objects pushing or pulling? Anything in the horizontal direction? No, right? Try not to overcomplicate your life, right? Okay, which way? Okay. Now that, so we are actually set. Our destiny is set for us. We said that acceleration for mass number 1 was up the slope, right? That's what we guessed. You want to stay consistent with that choice because there's a string involved, right? And the strings can only pull, right? So we cannot have the two accelerations being opposite of each other. So what does that mean? What do we have to pick for our acceleration for mass number 2? We must pick down. If mass number 1 is accelerating up the slope and mass number 2 is connected to it by a string, it must be accelerating downwards. So once you pick something, you got to realize, I always say you need to be consistent with your choices. Choose something, but then always stay consistent with that choice, meaning that you follow up, right? And you maintain directions and things like that throughout the problem. So that means that I'm going to go ahead and say that the acceleration is down. I'm still kind of guessing on that. So sometimes I put a question mark over the thing I'm guessing. And sometimes my page is nothing but question marks. And so, okay, which way is positive y? Look only at mass number 2. Which way is positive y? You're going to feel really uncomfortable. It's down. Positive y is always up. No, it's not. What do we do to stay safe? What's the rule of thumb? Be consistent. Always put a positive axis in the same direction as your acceleration. That's going to save you from minus sign errors as we go. So that means we are going to make positive y be down. And now you just give up on everything, right? Because now, I mean, rotating coordinate systems is one thing, Mr. Balogh. Inverting them completely, right? And saying positive is down, maybe that's a bridge too far. Tristan? That's the only way that you're going to not make a negative sign error, yes. Follow your acceleration. It makes the next parts easier. There are other ways to do these problems, but this generally is the way you will see in almost every physics classroom at this level, most physics textbooks, right? This is the preferred way. We could start, getting all kinds of neuroses around negative signs, which you might already have, right? But this actually flows a lot better. Okay, we visualized, right? Now what do we do? What's the next step after visualization? Strategize. And in the strategy for Newton's second law type things, that means we're writing down equations, doesn't it? We're going to go and we're going to start with the master equation and realize that we need both horizontal and vertical directions. But how many objects do we have? We have 2. So maybe, just maybe, I'll organize things by saying, look, okay, we're going to do mass 1 over here, and we're going to do mass 2 over here. And there's going to be an x direction equation and a y direction equation, right? Because Newton's second law in vector form becomes everything x direction separated from everything in y direction, right? And we're going to do the same thing over here for mass number 2. So worst case scenario, how many equations are we going to end up with? 4. One equation becomes 4. Newton's second law applied to both objects in both directions that we are concerned with. Okay. To do this should we just do mass number 2 right now and get it out of the way? Because mass number 2 is pretty straightforward. Does anybody notice? How many vector components do we need to find for mass number 2? 0, right? Everything lines up, doesn't it? With our vertical direction, because everything's just vertical. So, that's nice. I can just write MAY equal and MAX, right? So that's what Newton's second law starts with. And in the x direction, how many forces are there? Oh, I like zeros. Zero's good. Zero's happy number, right? Okay. What is the acceleration in the x direction? 0. Why is it 0? Because we lined up the y-axis with our acceleration. If our acceleration is completely lined up in the y direction, what does that automatically make the x direction? 0. So 0 equals 0. Easy equation to deal with, not very useful in the long run. Okay, so that leaves MAY. How many forces in the y direction? 2 of them. They are M2G and T. Very carefully tell me what direction is M2G pointing, positive or negative? Positive. Why is it positive? It's pointing down, and we said that down was the positive direction. Which way is T pointing, positive or negative? Negative. Notice I didn't ask you which way is it pointing, up or down, right? Positive or negative. It's pointing in the negative direction because the positive y direction is pointed down. You're like, Mr. Balogh, that's breaking my brain. Good, it's breaking, brain breaking here is good. But trust me, that method, you make less mistakes over time dealing with the signs over here than forgetting the sign over there. Promise you. Okay, so that's that one. All right, so to be able to pull this off for, and I'm being sloppy again. Jeez, Mr. Balogh, wake up. M2, there we go. All right, so to be able to pull this off with M1, we need to fix something. What do we need to fix? We can't write down our Newton's second law until we do what? We need to find components of at least one of these forces, right? What can you tell me about the normal force? Are there any components to find? No, right? It's lining right up along the y-axis, isn't it? What about the tension? Do we need to find components of the tension? No. So that leaves the weight, right? So we do what we did before, right? When we had the cow? It was cow, wasn't it? Yeah, okay. We had the cow on the hill, right? We know that we have to go down the hill and into the hill to find these components. Assuming that we can get information about the angle of the hill, where does that angle show up? Right up there? Which makes the side touching the angle, which trig function? Cosine. So mg cosine theta here, mg sine theta there. Broke that mg, and it's m1s, good grief. It's m1 g's, right? Because that's the hypotenuse. And then I've got the 2 components. All right, so in the x direction. So now we're going to laser focus on this line right here. How many forces lie in the horizontal direction? It's like 2. They're sitting right there, aren't they? So that's going to be T and M1G sine theta. Now I go back and ask the question, what direction are they? T, positive or negative? Why is it positive? Not because it's pointed up the slope, but because up the slope is the direction we said was positive, right? Because I said so. All right, m1g sine theta. Pointing up or down the slope, positive or negative? Negative. Okay. Y direction. Looks like we have a normal and an m1g cosine theta. Normal force, positive or negative? m1g cosine theta. All right. So we have managed to visualize for sure. Strategy starts with getting the equations written out. This is the part where we develop the toolbox, right? We've come up with a system of equations, and now we need some insight as to what we're looking for, right? Probably looking for acceleration of the system or tension in the wire, or maybe both. Could be a part A and a B problem, right? So those generally would be the things that we are looking for. I'm trying to keep this as generic as possible, right? Maybe we could go looking for normal force and things like that. But now we need to strategize. Now we need to ask ourselves, okay, how are we going to get from where we are to where we want to be? Assuming that we were given, right, the angle and the masses and the planet that we're on. Okay? So if we know our angles and we know our masses, like when you look at this term right here, what is that? m1g cosine theta. What do we know about those three things? We know all of them, don't we? So that's just a number, isn't it? Not much we need to do there, right? Okay. M2G, that's just a number. No unknowns in it, right? Okay. M1AX, that's unknown. M1AY. Actually, we do know something about AY, don't we? For mass number 1. It's 0, isn't it? Why is it 0? We made sure it was 0. How did we make sure it was 0? What rule of thumb did we follow? Always put one of the directions, x or y, in the same direction as your acceleration. So if we choose x, positive x, to be in the same directions of our acceleration, what does that automatically mean for y? 0. Okay. Which means that this equation right here just is normal force equals m1g cosine theta, but we didn't want to know anything about normal force, so that was a waste of time. Okay, it wasn't. It's coming up next chapter. Okay, so what are we left with? Looks like we have this equation and this equation. I drew boxes. They're not the end goal. They're a starting point, okay, but I wanted to highlight them. They're really the only 2 equations that can tell me anything about acceleration and tension. So now I have a math problem. I have a problem where I've got 2 equations with 2 unknowns. I mean, I know one of them says AX and the other one says AY. But what can you tell me about the acceleration up the slope and the acceleration down on the hanging mass? It's the same. If the string isn't breaking or stretching, right, then AX is equal to AY. And away we go. So, how do we solve this? How do we find A and T, 2 unknowns, if we have 2 equations? There's lots of different ways you may or may not have been taught in high school or paid attention in high school, algebra class or whatever, right? It's 2 equations with 2 unknowns. So you just go for it, right? I think what I'm going to do, I'm going to solve this one for T. This is going to be M2G minus M2A. What the heck did I do there? I know it looks like a mystery. I know I don't spend any time on math in here. But if I move t over the other side of the equal sign, what happens to its sign? Switches, doesn't it? Like adding t to both sides. And if I move a positive thing across the equal sign, what happens to it? Becomes negative, right? So that's exactly what I did. Okay, that t, now that I have figured out what it is going to go up in here. And then I can rewrite this equation down here. Now, every math teacher in the world just died because I'm drawing arrows. My math teachers taught me that I was never allowed to draw arrows on my math work. Guess who's in charge now, Mrs. Davis? All right, so let's see here. This is going to be M1A equals. And then in the place of t, what am I going to write? Yeah, I've got this thing over here. I solved for t. I know what it is. It's M2G minus M2A. So now I'm going to do M2G minus M2A. That was the t, and then minus M1G sine theta. Okay, 1A. A is the only unknown I have in here now, right? So I'm going to move the M2A over to the other side of the equal sign. M2A is negative. If I move it over, what happens? Becomes positive. I'm left with all this junk on over here. That's just a number. M2G minus M1G sine theta, just a number. And with this A being in two terms on the left-hand side, how do I get it to be all by itself? Factor it out. There was a reason for learning factoring. Yeah, but that's as far as it goes. All that other factoring that made you learn, pointless. M2G minus M1G sine theta all over M1 plus M2. And there we go. We solved for A. I did skip a lot of math steps in there, but this is not a math class, right? Whew! Okay. What did we have to do? We started with a simple picture and it went really bad pretty quickly, didn't it? And there's so many moving pieces here, isn't there? You've got to remember signs. You've got to remember rules like accelerations and positive x and y's. And then you got to write down equations and then you got to solve equations, right? I honestly believe this is peak difficulty in this class. We are asking you to do a lot, right, for just one problem. And we haven't even solved for t yet. We've only solved for A. How would you solve this for t? Actually, I've already done it. This is a number now, isn't it? These are all known things. So I can just plug it back up into there to get t, right? So, personally, totally up to you and your mathematical, how you were taught and all that kind of stuff. I personally find eliminating t to be easier. If you try to eliminate A first, you end up with fractions running around, which I'm afraid of fractions. They did bad things to me when I was little. So I don't like. Was it fourth grade I started learning fractions? I didn't like fourth grade at all. It was a bad day. All right. So again, the fact that this is down here in the box is only useful if you have exactly this problem, right? What I wanted, the takeaway from here is the process. Process, process, process. Because for every problem, what are you inventing? The toolbox, right? You are inventing these equations up here that you will then figure out to solve for whatever they're asking for. And they could give you acceleration and ask you to find the tension. They could give you acceleration and tension and find a mass, right? Like after this, that's just math, right? But the setup, that process of analysis, of looking at what forces are doing to objects, that process is the same every time. All right, let's do another quiz. Chapter 6. Moving right along. And I know for the size and difficulty of chapter 5, that didn't feel like enough time. And you're not wrong. We could probably spend the rest of the semester just on chapters 5 and 6 alone. But we can't do that. Gotta move forward. So chapter 5 is a brutal homework chapter. Chapter 6 is a brutal homework chapter. They're long problems. And you've seen tastes of that already. You've seen the taste, like it just takes us a while to get these things set up. So what we're going to do in chapter 6, we're just going to add friction. That's all we're going to do. How bad could it be? We have been avoiding it, right? And there are reasons. There are reasons that we have been avoiding friction, because it starts making your life terrible. Okay, so let's see here. Friction. Friction is that force that exists between objects that kind of causes them to stick together. You guys know what friction is, right? But in engineering and physics, we do go a little bit deeper, and we talk about 2 broad categories of friction. And those are static friction and kinetic friction. Now, the word kinetic means what? Moving or motion, right? Something's happening. So the friction associated with motion, something sliding. When we say motion in the context of friction, kinetic friction, what we mean is motion between surfaces of contact. You can't have friction without 2 things coming into contact. If it's air in a car, that's still a surface of contact, right? But we tend to think of friction like maybe on the road surface, between the tires and the wheels, right? Between our feet and the ground, whatever the case may be, right? So I want you to do an experiment right now. I want you to take your hands, I want you to put them together like this, and I want you to rub up and down, right? What do you feel? You feel heat, right? But beyond the energy considerations that we'll talk about next chapter, you are experiencing kinetic friction. You can stop now. Or keep going, whatever floats your boat, right? You are experiencing kinetic friction here. And why is this kinetic? Be careful, it's not just because it's moving. What is moving? 2 surfaces relative to each other, right? Okay? So what does that mean static friction is? It's friction when 2 surfaces are not moving relative to each other. Same experiment. Bring your hands together in front of you. Now I want you to push up or down, but don't let your hands move. Like apply enough pressure inwards so that when you try to slide up or slide down, it doesn't go anywhere, okay? You have now caused static friction to happen. And why is it static? Because what's not moving? The surfaces relative to each other. And this is where, so kinetic friction is pretty easy. And our brain gets a little bit of relief here because you know something has kinetic friction if it is sliding or moving relative to the surface of contact. Easy, okay? Static friction, however, isn't as straightforward. Static friction can come and bite you, and static friction really is just evil, okay? Let me see if I can demonstrate some of this for you. Let me take binder and my stapler. Okay. If I put my stapler on top of my binder and I walk across the room like this, okay? Static or kinetic friction between the stapler and the binder? This is static friction. But wait a second, Mr. Bay, you said if it's moving. Not just the fact that the object is moving. What's really important? Relative to each other, right? Is the stapler in contact with me at all? No, right? It's in contact with the binder, right? And so the friction exists between the stapler and the binder. Do we need to sing the song? Right? Okay, so we look at that surface of contact, and if those 2 things aren't moving relative to each other, What kind of friction is it? Static friction. Now, if they move relative to each other, what kind of friction was that? That was kinetic, right? Because I jerked it out so fast, right, that it was kinetic friction, not static friction. So, if you are, well, let's do it this way. What kind of friction exists between the tires of your car and the road surface? Kinetic or static? For maximum safety, well, you guys go straight to all the extremes. For maximum safety, what kind of friction do you want to have, static or kinetic? If there is kinetic friction between the tires and the road, what does that mean? It means the surface of the tire and the surface of the road are moving how? Relative to each other. In other words, you're in a skid. Okay? So that means that if you are not skidding or sliding across the surface of the road, what kind of friction is it? Static? But Mr. Balogh, I'm moving, the car moving, the wheel on the bus goes round and round, right? Like, why can you tell me? The patch of contact between the ground and your tire as it comes around, what's the relative motion between your tire and the ground? 0. Don't know how to break it to you, but that's static friction. Okay, walking across campus. This is the first time I've tried standing on these tables. It's going to be fun. Okay, woo, surfing. All right, as you walk and you plant your foot, right, and you take a step forward, static or kinetic friction? Static friction. Why is it static? Because if it's not static, then you are slipping or sliding and you're about to be embarrassed in society, aren't you? Right? Okay? Or you're ice skating, one of the two, right? Okay? So this is static friction, right? You plant your foot. What direction is the force of friction on me? Your choices are forwards or backwards. What direction is the force of static friction on me as I take a step forwards? I think we really need to sing the song. Plant my foot. Which way does friction push on me? Which way does my motion change? Forward. Which way was the force on me? Forward. Friction pushed forward on me. Which way did, when you put your foot down, which way are you pushing on the ground? Backwards, right? So you concentrated on the other force, right? You pushing on the ground. It's not what I asked, right? I asked, what is the force of friction on me, right? And the only direction that can be is forward. If I push backwards on the ground, then finish the song. The ground pushes forwards. I mean, we changed the song a little bit there, right? Okay. That's Newton's third law, isn't it? So can static friction make things go? Yes. Can static friction make things stop? Yes. Can kinetic friction make things stop? Baseball. American baseball. You're sliding into second base. I know enough about baseball to know you don't slide into first. Okay? You're sliding into second base. What happens to the speed of the runner and slider? Goes from moving to stopping. Can kinetic friction cause you to slow down? Yes. Can kinetic friction cause you to speed up? Kinetic friction always acts against the direction of motion. That's like the certainty in friction that you can take home with you, okay? Kinetic friction will always act against the direction of motion. So if that baseball player is sliding into second base, sliding, right? They are moving relative to the surface of the baseball diamond, right? They're sliding into second base. Which way is the force of kinetic friction pointing? Toward second base or away from second base? It's away from second base because kinetic friction always acts opposite the direction of motion. Yeah. Walking, are we sliding when we are walking? I will now attempt the moonwalk by Michael Jackson. No, I won't. Okay? We are not sliding when we're walking, right? We count on not sliding. Anybody that's tried to walk on ice knows what happens when you have no more static friction. Okay? So static friction in that situation is causing you to move forward. Now, static friction can also bring you to a stop. Can anybody give me an example of where static friction is bringing you to a stop? Braking on your car. Your car probably has something called an anti-lock braking system in it. From the name, what do you think an anti-lock braking system does? Stops your wheels from locking, meaning that they're no longer rotating. Because if your car is moving and your wheels are no longer rotating, what kind of friction exists between your car's tire and the road? It's kinetic, okay? However, an anti-lock braking system keeps your wheels turning, maintaining static friction between the surface of the road and your tires, which turns out to have very big safety benefits because a car equipped with an anti-lock braking system has a much shorter stopping distance than a car that doesn't. You got a car where wheels just lock up, you will just be sliding, okay? And kinetic friction, its maximum is always less than the maximum that static friction can exert. Static friction will always win. And you've experienced this if you've ever had to move a heavy piece of furniture across like a carpet or something like that, right? You got like a couch or the entertainment center or whatever, you go to like start pushing on it and it's like really hard to get it to start. But as soon as it slips, it's a little bit easier to push, isn't it? That's because you overcame what kind of friction? It wasn't moving. That was overcoming the static friction, right? But once it was in motion, kinetic friction's maximum is less than static friction's maximum, always. Static friction, though, can change its amount. Static friction wants to keep the two surfaces not moving relative to each other, right? And so it will change the amount depending on the situation, okay, to maintain that no motion of the surfaces. So static friction is bad. Static friction is bad. And if the static friction is in the problem, and how do you know static friction is in the problem? If the surfaces are not, oh, wait a second, we can say not moving now? I yelled at you last chapter for cueing in on motion, but now with friction in the mix, you do have to cue on motion. But it's not just the fact that the object is moving. What do you have to be careful to analyze? The surfaces of contact, are they moving relative to each other, right? So cardboard box in the back of a pickup truck. Static or kinetic friction as that pickup truck starts from a stop sign and starts going. That's static friction. Why is it static friction? Because the cardboard box stays, right, on the bed, right? If you accelerate too quickly and your tailgate's open, then you got kinetic friction. Okay, So how do we go about like writing all this stuff down and doing it? By the way, you guys are going to have nightmares for the rest of your life about penguins. I'm not sorry, but there's a homework problem in chapter 6 involving a penguin. This is going to drive you bonkers. Okay. The thing you have to remember about friction, the only thing that's really going to save you when it comes to friction is that you have to absolutely, positively remember, your life depends on this, that friction is fun. It's like the one big dad joke in physics, right? Okay. That little curly F is usually reserved for the force of friction. Different books do this different ways. Capital F, sub curly F, different way. I just go straight for the curly F. The N in that equation is normal force, the normal force that we've been talking about the whole time. Okay. So does that mean friction and the normal force are related to each other? Uh-huh. Yeah. More normal force, more friction, vice versa. Okay. And then there is the Greek letter mu. Among the other things that they didn't tell you we were going to learn in this class, it was the Greek alphabet. Okay? Because we're going to use this Greek letter mu. Mu is a letter that looks like our U. Right? There's a U. Okay? But the Greek letter mu, like kitty cat, right? Spelled mu. Okay? Has like a leading leg, like an elephant's trunk on the front of it or something like that, okay? I tend to, because I don't like picking up my pen as I write, I tend to go big on that first thing and then I kind of make the letter U on the end. So mine can get a little bit sloppy after a while, but yeah. No surprise there because my handwriting stinks. All right. So what is that mu? What are the units of F, the force of friction? Hint, it's a force. It's a Newton. What are the units of normal force? It's a Newton. And what happens if you divide a Newton by a Newton? Nothing. You get no units. So what are the units of mu? It's unitless. Mu has no units associated with it. I need newtons on the left-hand side. I need newtons on the right-hand side. And if I'm going to multiply two things together, one of them's already a newton. The other thing can have no units. So mu is unitless. It's called the coefficient of friction. Books, coefficient, I don't think I spelled that right. And books go to like big lengths to like draw mu sub s and mu sub k. What do you think they're trying to say? Kinetic or static? I usually don't bother. But just so you know, you'll see that symbology in a lot of different places. It's a number that kind of tells you how much friction there is between at the surface of contact. So like between your car tires and the road, it's like 0.4, somewhere in there. Ice is like 0.001. So the smaller this coefficient, the less friction there is, okay? The coefficient of static friction is usually a range. It can go positive and negative and zero and everything in between. Kinetic friction is always just a number, and we already know the direction that it points. It always points opposite the motion. But sandpaper will go over a coefficient of 1, right? It's really rough surface. But generally, these coefficients are between 0 and 0.8 for most. It totally depends on the surfaces coming into contact. Okay. All right. So that's how we're going to deal with friction. It's related to the normal force. Friction is fun. We have to remember this. So now we need examples, okay? And I went out and I tried to find examples everywhere, pictures on the internet that I could use. And the one thing that I always think of when it comes to friction and hills is slides, right? Because what's a slide? It's a hill, right? With friction. And then I found this. Americans aren't agreeing on a lot right now. But I find that there would probably be a majority consensus that we should have this. Right? Like, why is this not an option everywhere? You don't have to use it. If you're afraid of hurting yourself, you don't have to use it. This is brilliant. I'm all for this, right? So what makes a slide so fun? Whee! Right? Okay? Now, I grew up in an age when slides were made of metal. And everybody wore corduroys. And corduroy on metal was basically, it was a recipe for polished metal surface. Like, we were going for an effective coefficient of 0, right? At our playground. We tried everything. We tried adding oil to the slides. That ended up not working that well. And our moms got mad because we stole all the Crisco. We used pieces of carpet. Like we tried to find that industrial carpet that really doesn't have a pile, but it is like a fabric-y surface, right? Okay. And we would like polish the slides, trying to get that friction down to 0. Nowadays, they just put these plastic slides into places, and the only fun you can have there is watching your kid's hair stand on end as they build up static electricity all the way down, but they go too slow. It's not fun. Don't call CPS, okay, right? I believe in protecting children and all that kind of stuff, but come on, there's got to be some danger at the playground. Otherwise, you're not learning anything. Okay, so let's do an inclined plane with friction. We're going to get this one started in the setup, and we're going to have to finish it next time, okay? So you see the words inclined plane, and what do you picture? A triangle. So this could be a slide, it could be a loading ramp, it could be a wheelchair ramp, right? Anything that's tilted up at some kind of angle that we hopefully know, okay? And let's go ahead and put our cow back on this hill, right? The cow last time was on an icy hill, wasn't it? So this time we're going to put the cow on a normal hill, and we're going to include friction. Let's just see how it changes. Right? Let's just see what the differences are here, right? So we come in, start asking ourselves, okay, let's see. We got the weight of the cow. We've got the normal. Does anybody disagree with those two forces right now? I am literally like copy pasting, right? From our cow example that we did last week, okay? Let's say that the acceleration is down the slope. And that means I'm going to put positive x down. If you go back and if you look at any of the notes, mine or yours, you'll see this is exactly what we did last time for this particular thing. Okay. However, and that was where we left off, right? And you guys wanted to keep drawing forces that weren't there, right? And we know that there's going to be components here, right? But before we get to the components, now that friction is a part of the mix, I need to tell you whether or not this cow is sliding down the hill. And I think I already said that the cow is sliding down the hill, right? Okay. So we're going to have the cow sliding down the hill. Now that word sliding tells you right away what kind of friction we're dealing with. It's kinetic. It's sliding down the hill. The cow is in motion with respect to the surface of contact, the hill. So what does that mean for the direction of the kinetic friction? If the cow is sliding down the hill, and in this case, speeding up, right? The acceleration is positive down the slope, right? Then what direction is the friction? Up the slope. Okay, so we come in here, we think about our coordinate system that we've identified, something like that. Right? And we find that we need to go get components. Do we need components of F? How neatly it lines up, right? By the way, F and normal force are always perpendicular to each other. The normal force is perpendicular to the surface. The force of friction is the force in the plane of the surface of contact. So the surface actually gives two forces now. It gives normal and friction. And then we've got this one. And so we're going to have mg sine theta and mg cosine theta. And away we go, right? All we've done is add one force. That's it. One force, right? In the x direction, before we had ma equals, and it was just mg sine theta. That's where we stopped last time, when we had no friction in the problem. But now we have a second force. We have the force of friction. What sign do we put on mg sine theta? Positive or negative? Positive. Why? Same direction as what we said was positive, which was down the hill. What sign do we put on the friction? Negative. Why are we putting a negative sign on the friction? It's opposite the direction we are calling positive. We called positive down the slope, and so friction is pointed up the slope, so it deserves a negative sign. That's it. This negative f is the only change in all the equations I'm about to write. Because in the y direction, we had ma, but the y direction is 0, right? Equals mg cosine, it was normal minus mg cosine theta. Oh, I might finish this one. Okay, so again, our change from the Cal problem last time is just this minus friction that's in that term up there, right? So now we solve for the acceleration again. We solve for the acceleration having been given the mass of the cow and the angle and the planet that we're on and the coefficient of friction since there's friction involved now, okay? So how do we solve for the acceleration now? How many unknowns are there? 1, 2, 3. I have 3 unknowns in my equations, in my toolbox. What? We have an extra equation? There's not just 2? What's the extra equation? You've forgotten how much fun friction can be. You guys are going to get so sick of that. Right? Friction introduces fun to our problems. And what does fun let us do? Do you see it? Can we solve the normal force and stick it in there? And then can we take this F and insert it in there? And then will we have eliminated 2 out of our 3 unknowns? You betcha. Let's do that really quick. Killing math teachers as I draw arrows. I love it. Mg sine theta minus, and then this is mu times n, because I insert it right. F equals mu times n. And now what does n equal? That useless equation from last chapter that we always seem to write down but never used. Well, why was I writing it down so often? Because I knew we were going to use it. Right? It was coming. Right? So that goes in there. Ma equals mg sine theta minus mu mg cosine theta. And now can I divide by m? I mean, I can't always, but what's the magic here? It cancels out. Why am I allowed to just cancel these out? They are in every term, right? If I divide every term by m, it all becomes ones. Okay, so that means my acceleration is g sine theta minus mu g cosine theta. And how do I check that? There's an obvious check, hopefully, that jumps straight to the forefront of your mind Something that we can put to 0 that would make our lives a lot easier. Not the theta, even simpler than that. The mu. Because if mu is 0, how much friction is there? 0. And what do we have? We have exactly the same thing we got with the cow when there was no friction, right? So we already know the form of our answer is obeying what happens if we don't have friction, right? If we put friction back in the mix, notice the sign we have between these two terms. What will friction do to the acceleration if mu is not 0? It will take away from the acceleration. Is that what friction will do for us? Will friction make it so that it's harder for this thing to accelerate? Yeah, it's sliding down the hill. It's exactly what it's going to do. So I like the sign, and I like the functional form of it. Okay, then we can play all kinds of games with like zeros and 90 degrees and all that kind of stuff, right? But I have a feeling that this functional form is correct because it seems to be obeying the simpler version we had before, right? If I had had a plus in there, I might be a little bit worried, right? Because that would suggest to my mind that friction's helping speed it up, and kinetic friction can't do that, right? All right, I'm going to leave you there, right? And I will see you tomorrow. Did everybody get a lab packet? I sent them out, right? If you didn't get a lab packet, come up here. But we're doing lab number 6 tomorrow, not 5, not the one on the front of the packet. We're doing lab number 6. I will see you then.